Okay, so here what we're going to look at is the concept of a function being periodic. Basically, by definition, as you can see here, a function is periodic if there's a positive number p, such that for every number x in the domain of the function f, x plus p is in the domain, and also f of x plus p equals f of x. So these numbers are the same for every x in the domain. And p has to be positive. Not only that, if there's a smallest such p, then we call that the period of f. So the smallest such p, it makes sense to say the smallest because by definition, p has to be positive. So the smallest such p, such that this holds, we call that the period of f. Now, we could spend more time on a function being periodic, but for now, let's just consider the trig functions. Now, if you remember, if you have an angle theta that's drawn in standard position, the angle theta plus 2 times k times pi, where k is any integer, positive or negative, those angles are all going to be coterminal. In other words, their initial and terminal sides will coincide with each other when drawn in standard position. So for instance here, let's draw, to help illustrate this, let's draw theta in standard position. Like so, that's what I'm doing. So here's our initial side. So again, let me label it. We have x, here's y. So let's say this was theta. Okay? What angle is theta exactly? Honestly, I don't know. But that doesn't matter for now. Now, if I were to consider theta plus 2 pi, right? What is that going to look like? Well, that's going to have the same initial side. Its terminal side, well, to draw the angle, you would have to do this. Let's see if I can draw it. So we have a full rotation, right? But the terminal side is going to be exactly the same. They're going to lie on top of each other. And really, that's just because a full rotation is 2 pi radians. An angle of 2 pi radians amounts to a full rotation. Same thing with 360 degrees. So from theta plus 2 pi, let me draw this in a different color now. If I were to draw theta plus 4 pi, let's say, in standard position, right? So what's going to happen now? Well, I'm going to do one full rotation, another full rotation, and again, I'm going to end up with the same terminal side. So the angle in red, see if I can draw it, this angle in red is theta plus 4 pi, which again is theta plus 2 pi, right? But then we're adding another 2 pi. And if you were to subtract 2 pi instead, the only difference is that you would rotate the other way. Either way, what I'm trying to say is all angles of the form theta plus 2k pi, they're coterminal with theta. Their terminal and initial sides are the same. Okay, well, what does that have to do with trig functions? Well, if you remember that when we have the unit circle, hopefully this won't get too complicated, hopefully the drawing will be nice, but if you have the unit circle, right, the way to get the trig functions of that angle, you look at the point P, which is on the terminal side, and on the circle. You know, that's going to have coordinates x, y. And what we're saying is that the P, which corresponds to coterminal angles, that point P is exactly the same. That point P is exactly the same. And because of that, what we have then is this. We have cosine of theta is x. Sine of theta we have is y. But if you take theta, but if you do cosine of theta plus 2 pi, you're going to get the same exact x, because that angle gives us the same point P. And sine of theta plus 2 pi, that's going to be the same y. Again, if you do theta plus 2 pi and theta and theta plus 2 pi, these angles being coterminal, the terminal side is going to be the same, hence the point P on the terminal side and the unit circle is going to be exactly the same. One more time, if we did cosine of theta plus 4 pi, right, that's also going to be the same x. And sine of theta plus 4 pi, that's going to be the same y. What is this really trying to show you here? I'm trying to show you, since theta was arbitrary, I'm trying to show you that sine and cosine are both periodic functions. And not only sine and cosine, but it also turns out that all the trig functions, the other ones, tangent, secant, they're all periodic functions. You could actually show they're periodic because sine and cosine are. Remember, you can express tangent, secant, all the other trig functions in terms of sine and cosine. Okay, so we know they're periodic, then naturally we want to know, or we ask at least, well, what's their period? It turns out sine and cosine are periodic with period 2 pi. Sine and cosine and secant and cosecant have period 2 pi. What may not be obvious at first, it does take a little bit of work, although it's not terrible, but tangent and cotangent have period pi. So let me say it again. Cosine and sine, secant and cosecant have period 2 pi. Tangent and cotangent have period pi. What I wrote down here, as you can see at the bottom, is for sine, cosine, and tangent. Okay? Now again, this is all in radians, okay? So in degrees, you would have sine and cosine would be periodic with period 360 degrees. Same thing with secant and cosecant. Tangent and cotangent would have period 180 degrees. Okay, now how does this help us? So what's the point of this? Well, what's nice is that if we want to really understand sine and cosine, it's really enough to work on an interval of length 2 pi. Really, because it's periodic with period 2 pi, instead of looking at the entire domain, it turns out we can learn everything about sine and cosine by just focusing on the interval from 0 to 2 pi, or really any interval of length 2 pi. With tangent and cotangent, the idea is similar, but instead, it's enough to focus on an interval of length pi. Because again, they're periodic with period pi. So any interval of length pi will do.